Object serialization is a new OPC UA core technology for data streaming. There are already established core technologies supported by OPC UA for data streaming, such as PubSub. However, when dealing with object hierarchies containing different OPC UA variables at different hierarchy levels, a compact representation of the data of interest would have substantial advantages for the consumer and the publisher of the data and would also improve client-server access. Object serialization specified in Part 25 enables servers the provision of structured data representations containing the values of different variables. It also specifies how these representations can be curtailed for various use cases, especially with respect to status information and metadata associated with each represented value. Object serialization is defined as the aggregation of the values of different variables into the value of a single variable. These variables belong to a subset of the information model, which is referred to as serialization scope. The aggregated value is called the serialization value and is the value of a single variable, which is called serialized data variable. When accessing the serialization value, clients gain access to all values in the serialization scope at once. On read or write access, the serialization process takes place. In case of read access, the values of the variables in the serialization scope are transferred into the serialization value. In case of a write request, all values aggregated in the serialization value are written to the original values of the variables in the serialization scope. A serialization scope is a subset of the information model consisting of the nodes reachable from a root node called the serialization start node. Any node can become a serialization start node when referencing a special object, the serialization entity, using the Haage serialization entity reference type. The serialization entity is the parent object of the serialized data variable providing the serialization value. The serialization entity object also has an interface for the configuration of the serialization scope. A set of properties of the serialization entity object comprises the serialization configuration, determining which variables of the subtree originating from the serialization start node take part in the serialization process. This subset of the information model forms a serialization scope configured by the serialization properties of the serialization entity. The serialization process creates a serialization value data type with serialization field data types for each value in the serialization scope. The serialization properties allow detailed curtailing of the serialization scope for specific requirements. The include reference types property tells the serialization process what reference types to follow when serializing the node tree. The exclude reference types property directs the serialization process to ignore nodes referenced with certain reference types. The serialization depth property limits the depth of the serialized node tree. Then consider sub-element serialization properties. Property allows the combination of serialization scopes configured in the same subtree of the information model. The custom metadata properties and custom metadata ref properties allow the specification of metadata for usage in PubSub scenarios. The include status, include source timestamp, and include dictionary reference properties determine if status information, companion values like timestamps, and other additional information like references to data and dictionaries shall be included in the serialization value. Here are some base properties, advantages, and features of the serialization model. The structure of the serialization scope is preserved. This means that the parent-child relationships of the variables and objects in the node tree are mapped properly. Since any node can become a serialization start node and can reference one or more serialization entities, servers can provide different serialization values for the same subset of the information model, as well as serialization values for separate subsets. If the serialization configuration defined for a serialization scope is not adequate for a subtree of the serialization scope, The serialization configuration can be adjusted for certain subtrees by referencing a serialization entity from the root node of the respective subtree. Serialization scopes can contain other serialization scopes with different serialization configurations. Servers can support the transaction logic. If the writing of one or more of the original values in the serialization scope fails, the original values are restored. Servers can also support data consistency for read access. Shows the result of object serialization when serializing the components of an object. The myObject object has two child variables and one property, and each of these children contains a value. This object references a serialization entity and therefore becomes a serialization start node. The myObject serialization instance of serialization entity type has the include reference types property set to hasChild. This selects all variables and properties. The values of the variables and properties in the serialization scope are mapped into fields of the serialization value data type. The field names equal the browse names of the mapped variables. The values themselves each have their own serialization field data type. Here the serialization field data types of the variables in the serialization scope equal the data types of the original values. This example shows how node trees originating from a container object are mapped into nested structure data types. The serialization process creates a serialization value data type with serialization field data types for each value in the serialization scope. The values of the serialized variables are mapped into structure fields, which have the serialization field data type created for the variable. The serialization field data type is a structure data type if the mapped variable has children, as it is the case for variable 1. The nested structure data type of the serialization value maps the node tree levels and reflects the hierarchy of the node tree. The serialization value data type is a structure data type with two fields for variable 1 and variable 2 as direct descendants of the sum container object. Since variable 1 has children, it is represented by a structure data type with a value field and a children field. The value field represents the value of variable 1 and has the same data type, which is int32. The children field is a structure data type and has as many fields as there are components of variable 1. The field names equal the browse names of the mapped variables. The data types of the fields are equal to the data types of the mapped variables. Unless the serialization property limits the depth of the serialized node tree, there is no limit of the number of nesting levels the serialization value data type can have, apart from limits applying for structure data types and server resources in general. The serialization value data type structure is generated by the server for a serialization scope with a variable having other variables as components, and one of these variables also has variables as components. The descent into the depths of the subtree originating from the serialization start node causes the serialization value data type to exhibit nested substructures mapping the corresponding part of the subtree, as shown before. On top level, the value of my variable is mapped into the value field, whereas the components of my variable are mapped into the my variable children data type children field. Since each field of the structure represents one component of my variable, the two fields are variable 1 and property 1. Since variable 1 has children itself, it is represented by the variable 1 data type structure with an int32 value field for the value of variable 1 and a variable 1 children data type children field for the descendants of variable 1. This children structure field has an int32 variable 1.1 field representing the value of variable 1.1 and a duration property 1.1 field representing the value of property 1.1. If all subcomponents in turn had subcomponents themselves, which means great depths of the subtree, the recursive descent when constructing the serialization value data type is limited by the serialization configuration. by limitations of the structure data type or finally by the server resources. This example shows the impact of the include status, include source timestamp, and include dictionary reference serialization properties on the serialization field data type of a single variable. If the include status, include source timestamp, and include dictionary reference properties are all false, the serialization field data type of the variable equals the data type of the variable as shown in the left column for V1 type. If one or more of these include properties are true, the serialization field data type of the variable is a structure data type. The structure contains a value field which has the same data type as the value of the variable. Dependent on the value of the include properties, the structure can contain a status field with a data type status code, a source timestamp field with a data type UTC time, and a dictionary reference array field with one or more elements, as shown in middle and right column for the V1 type serialization field data type. This example shows how the components of the OPC UA channel group config object are mapped into the serialization value data type. If the serialization properties have default values, the properties of the channel group config object are mapped into fields of the serialization value data type, which have the same data type of the properties they represent. The JSON encoding of the structure only contains the field names as keys and the values of the serialized fields as JSON literals when using verbose encoding and raw data field encoding in a PubSub scenario. The enumeration values are encoded as string literals as specified in Part 6. This figure demonstrates how metering point objects and energy measurement values in an information model according to OPC UA for Profi energy can be serialized without the constant metadata associated with each node in the serialization scope. This serialization scope is configured to exclude the metadata properties of the objects and variables reachable from the serialization start node. The energy measurement type object has a mandatory P object number property, which is not part of the serialization scope, since the exclude reference type serialization property contains a has property reference type. The same applies to the PE measurement ID, accuracy domain, accuracy class, and engineering units properties of the measurement value type variables. The serialization value data type structure contains only fields for the values of the measurement value type variables. The JSON snippet shows how the energy data in the serialization scope are serialized using verbose encoding and raw data field encoding in a PubSub scenario. Here can be seen how a serialization scope configured by the serialization entity referenced by the energy management folder is modified by a second serialization scope. The consider sub-element serialization property set to true directs the serialization process to evaluate the serialization properties of the serialization entity object referenced by the measurement y1 variable, which is already part of the enveloping serialization scope. The include status serialization property of the second serialization entity is set to true, causing the status code of the measurement y1 variable value to be part of the serialization value data type. The exclude reference types array containing one element with the value has property reference type excludes all properties of the measurement 1 variable. The JSON snippet shows how the resulting serialization value structure data type is serialized using verbose encoding and raw data field encoding in a PubSub scenario. If the status code of the measurement y1 variable value is good, an empty status is generated by the encoder. If the status code is uncertain or bad, the status code and the corresponding symbol are generated by the encoder. In contrast, the status code of the measurement x1, measurement x2, and measurement xn variables values is never encoded into JSON. Here can be seen how nested value trees are mapped into nested structures. The serialization entity referenced by the serialization start node directs the serialization process to follow only Haage output channel reference types. The serialization process includes a channel object referenced with Haage output channel reference types and the components of these objects into the serialization scope, since each channel object references a serialization entity modifying the serialization configuration to include nodes referenced with a Haage component reference type. The resulting serialization value data type structure maps all hierarchy levels of the subtree with nested substructures and covers all components of the channel objects. JSON snippet shows how the values in the serialization scope are serialized using verbose encoding and raw data field encoding in a PubSub scenario. In PubSub scenarios and similar data streaming use cases, frequent transmission of unchanged metadata like engineering unit is not desirable, as it increases bandwidth demand. Since there are variable types exhibiting semantic properties like engineering unit or value range, the possibility to strip off these semantic properties belonging to the variables mapped into the serialization scope would be useful, since metadata need not be always read together with the data unless it has changed. As shown here, the serialization configuration excludes the metadata properties attached to the energy measurement type objects as well as to the measurement value type variables. The possibility to add the metadata to PubSub configurations to be conveyed to the subscriber with dataset metadata messages would be useful, or it even required. This figure shows how semantic properties can be added to the field metadata structure, describing the serialized data variable if added to a PubSub dataset. Each level of the variable tree is represented by key value pair array elements with a key equal to the browse name of the variable on the mapped tree level and an array of key value pairs as value. These arrays contain key value pair array elements for the semantic properties of the represented variables with the keys equal to the browse names of the properties such as engineering units and the values of the semantic properties themselves as value. If the represented variable has variables as components, and these variables also have semantic properties, they are themselves represented as key value pair elements of the parents array, with the keys equal to the browse names of the child variables and arrays of key value pairs as values of these elements, as shown for the measurement variables. This figure shows the resulting JSON encoding for the properties field of the field metadata structure according to the figure on the previous slide. The amount of metadata associated with the pure data exceeds the data values it describes by far. The JSON snippet only shows the metadata for two variables, and it demonstrates the usefulness of excluding the metadata from the serialization scope, especially for low bandwidth requirements. Let me summarize the topic for you. As the demand for data from the field level increases, the requirements for mediating technologies like OPC UA increase also. Object serialization meets these requirements and the challenges by addressing the crucial issues, such as bandwidth limitations or the need for status codes. The data transmitted can be stripped off the metadata while preserving the possibility to gain access to semantic information if needed. Moreover, distributed but related data can be aggregated into one transmitted unit, which greatly serves data consistency and integrity. Thank you for the attention.